What is antimatter? Essentially, antimatter is nearly identical to regular matter. It has all the same properties except opposite charge. British physicist Paul Dirac first discovered this in 1928 when he proposed an equation to describe the behavior of an electron moving at a relativistic speed. In the same way that the equation x squared equals 4 has two solutions, so did Dirac's equation, one positive and one negative. This led him to the conclusion that for every particle, there exists a corresponding antiparticle with an opposite charge. If antimatter collides with regular matter, they immediately annihilate in a violent release of energy in the form of gamma rays. Antiparticles can bond together to form larger particles in the same way that regular matter does. For instance, antiquarks can form antiprotons, which can then bond together with positrons to form antiatoms. What uses does antimatter have then, you ask? Well, as of today, gamma rays emitted from the annihilations of positrons and electrons are used in PET, positron emission tomography, a medical imaging technique to diagnose diseases and reveal tumors. Some researchers also believe antimatter can be used in fission reactors and even potentially power spacecraft. So, where can we find antimatter? Well, hardly any antimatter is seen naturally in the universe. Therefore, our only way of observing and studying antimatter is to create it ourselves. In particle accelerators, such as the Hadron Collider at CERN, antiprotons are spontaneously produced in high-energy particle collisions. Additionally, it has been discovered that some radioactive isotopes emit positrons naturally as a form of radioactive decay. This process is known as beta plus decay. These positrons can be combined with antiprotons to form antihydrogen atoms, which are then trapped in magnetic fields to be studied. Still, the longest period of time antimatter has been contained is 17 minutes. The challenge is that antimatter can't come in contact with anything, not even air, or else it would annihilate. Additionally, the process of making antimatter is very costly and requires much more energy than we get back. Therefore, its current use is limited and much more research is needed. Which brings us to the final point of the video. The world around us is full of matter and almost no antimatter is seen naturally, as mentioned earlier. The Big Bang should have created an equal amount of matter and antimatter, which should have then annihilated each other until nothing would have been left except for energy. But, as we see today, that's not the case. No one knows why the Big Bang created more matter than antimatter. But whoever will answer this question will solve one of physics' greatest mysteries.